Okay, let's dive in. We've got this new model creating some Buzz Seedance 1.0 from ByteDance Seed. You've got some really interesting sources for us today, kind of peeling back the layers on the tech.
That's right. I mean, video AI has come so far, but there's still this, tricky balance.
Mhm.
Getting the model to actually do what you ask, making the motion look real, not janky, and just, well, making it look good consistently. Seedance 1.0, based on this material, is really positioned as their shot at cracking that code.
And that's exactly what we're digging into today. We're going to go deep on the materials you shared, really focus on the, let's say, the academic smarts and the core technical ideas that they claim make Seedance 1.0 special. It's not just about cool demos, right? It's understanding the engineering underneath.
Absolutely. We'll look at how they handle data, which is always fundamental, their specific model architecture choices, some clever post-training stuff they do, how they make it fast, that's a big one, and then, yeah, how it actually performs according to their evaluations.
All right, data first then. It always starts with data. The sources really stress how vital this is. So what kind of video are we talking about, and how do they, whip it into shape?
Yeah, it's huge. They start with just a massive pool of diverse video, all sourced legally and ethically, they emphasize. But, just having a lot of data isn't enough. The interesting part, according to the sources, is their whole pipeline for curating it. It's pretty involved.
Okay, walk me through it. What are the key steps? What makes it different?
Well, think of it like prepping ingredients for a gourmet meal. First, diversity sourcing. They're not just grabbing random stuff. They actively look for a variety of different subjects, action styles, camera moves, the works, trying to give the model a really broad education.
Makes sense. Avoid bias, get generalization.
Exactly. Then, shot-aware temporal segmentation. Videos can be long, right? So they chop them into smaller bits, usually under 12 seconds. But crucially, they do it smartly, trying to keep whole actions or scenes intact within those segments. So the model learns coherent chunks of action. Visual overlay rectification, that's basically cleanup. Getting rid of watermarks, logos, burnt-in text. They sometimes crop cleverly to do this. You don't want the model learning logos. You want it learning the actual scene.
Right, the important stuff.
Then, quality and safety filtering. This is huge. They use other AI models to automatically ditch low-quality stuff, blurry, shaky video, bad lighting, and just as important, they use strong filters to remove harmful or unsafe content. That's just table stakes for responsible AI now.
Not negotiable.
After that, semantic deduplication. So imagine you have tons of clips that are almost identical. They use AI embedding, sort of like content fingerprints, to find these near duplicates and keep only the best or most representative one. This stops the model from just memorizing the same thing over and over, keeps the data set efficient and diverse.
Smart. Avoids wasting training time.
Precisely. And finally, distribution rebalancing. Real-world data is messy. You might have way more videos of cats than, say, kangaroos. So they analyze this distribution and tweak the data set. Maybe they use fewer cat videos or find ways to include more kangaroo videos to give the model a more balanced view of the world, fighting that inherent data bias.
Wow, okay. That's a serious amount of effort just on the input data. But the sources also mentioned this precision video captioning system. Sounds pretty critical for getting it to follow instructions well, yeah. How's that work?
This is really key for the prompt following aspect they emphasize. It's about linking language to the video content with extreme detail. They call it a dense caption style. So not just a dog runs, it's more like golden retriever joyfully bounds across a sunlit park, medium shot, camera tracking smoothly, capturing dynamics the action camera moves, and statics the subject, the scene.
Much richer descriptions.
Exactly, and the innovation described is how they get these captions. They fine-tuned a powerful video understanding model called Tarsier 2, using detailed, human-annotated examples of these dense captions. So Tarsier 2 learns to generate these super detailed descriptions automatically for their vast video library. This creates that tight link, user prompt, dense caption, vase video generation. That's reportedly a big reason for the improved instruction following, especially for complex sort of cinematic prompts.
That makes a lot of sense. Okay, meticulous data, smart captioning. Let's pivot to the engine room, the model architecture. What are the main parts? Maybe start with the VAE.
Right, the VAE, Variational Autoencoder. It's pretty standard tech in these kinds of models now. Its main job is compression. Think of it like a super smart video codec. It takes the raw pixel data, which is massive, and squishes it down into a much smaller, latent representation. The actual generation, the diffusion part, happens in this compressed space, much more efficient.
And then it has to unsquish it at the end.
Exactly. The VAE decoder takes the generated latent code and turns it back into the final video pixels. Now, they build on work like MagVit, using a VAE that handles both space within a frame and time across frames together. The sources mention specific compression factors they landed on, trying to find that balance between reducing size and keeping important details. One detail is they ditched an older step called patchification on the diffusion transformer side, simplifying the connection. And they trained the VAE using a mix of loss functions, L1, KL, LPIPS, even adversarial ones, basically different ways to measure how good the decompression is, focusing on sharpness, structure, and how humans perceive quality.
Okay, VAE handles the squishing. The main generation happens in the diffusion transformer, or DIT. What's new or innovative there, according to the sources?
This is where they've layered several interesting ideas, mostly aimed at handling video's complexity efficiently. First big one. Decoupled spatial and temporal layers. Instead of one giant attention mechanism trying to figure out everything at once, pixels within a frame, pixels across time, they split the job. Some layers only look at relationships within each frame, spatial. Other layers only look at relationships across frames, temporal. This specialization, plus using windowed attention so layers don't look at everything, makes it way more computationally feasible for longer videos.
Dividing the labor. Makes sense.
Yeah. And the overall structure follows the MMDIT architecture, which stands for Multimodal Diffusion Transformer. Similar ideas are in models like Stable Diffusion 3. It's built to handle multiple types of input specifically, visual information, and text prompts. They mainly blend these in the spatial layers using separate processing paths because, well, pixels and text words are very different kinds of data.
Okay. And you mentioned multi-shot video generation earlier. How does the architecture enable that?
Right, that ties into a specific innovation they call multi-shot MMROP. ROPE, or rotary positional encoding, is how these transformers understand sequence order. They developed a 3D version for video, height, width, time, and adapted it for both visuals and text. The really clever bit, as described, is how they use this ROPE to encode the positions and relationships not just of pixels or frames, but of entire distinct shots concatenated together. This allows the model to learn the temporal structure between shots, making coherent multi-shot sequences possible from one prompt. That's a big step for cinematic control.
That is clever, treating shots as sequential units.
Exactly. And finally, there's the unified task formulation. This is about flexibility. The same core model architecture is trained to do text-to-image, T2I, text-to-video, T2V, and image-to-video, I2V. They manage this by how they feed data in, using special masks to tell the model, okay, this part is a starting image, or this part is just noise, start from scratch. Training jointly like this apparently makes the model more robust and versatile overall.
That's a lot packed into the architecture. But training isn't the end, right? The sources mention these carefully optimized post-training approaches. What happens after the main model is built?
Right. This is about refinement, tuning, aligning it more closely with what users actually want and need. It's like sculpting the raw output, and it's multi-stage. First, prompt engineering, PE. We talked about those dense captions the model likes. Well, users type simple prompts. So they built another AI model based on a large language model specifically to translate user prompts into that dense caption format. They trained it first with examples, supervised fine-tuning, and then used reinforcement learning, specifically DPO with LoRi, to make it better at accurately capturing intent without hallucinating details. This PE model is like a smart translator sitting between the user and the video model.
Bridging the gap. Okay.
Then there's progressive training. Instead of throwing the hardest possible task at the model right away, like high-res, high-FPs video, they start simpler, maybe just T2I first, then low-res video at 12 piece, then higher res at 12 piece, then finally full res at 24 fps. Each stage builds on the last. It's more efficient for training and helps stabilize learning.
Makes sense. Like learning levels.
Kind of, yeah. They also have a continued training CD phase, specifically to boost image-to-video performance, giving it more I2V examples after the initial pre-training, and standard supervised fine-tuning, SFT, using high-quality prompt video pairs, often human-verified, to really hone the output quality and style alignment. They even mention merging models trained on different high-quality subsets, a technique to combine strengths.
Okay, lots of fine-tuning. But the sources make a big deal about RLHF, Reinforcement learning from human feedback.
Yes, RLHF is a core part of their alignment strategy. It's about directly teaching the model what humans prefer. They collect data where people compare generated videos and choose the best worst, sometimes based on specific criteria like motion or realism.
And they do something different with the rewards.
Yeah, this seems to be a key innovation. Instead of one single quality score, they built 3 specialized reward models. Think of them as AI critics with different expertise. One looks at fundamental stuff. Does it match the prompt? Is the structure okay? Another is purely focused on motion. Is it smooth? Are there weird artifacts? The third is an aesthetic critic. Does it just look good, visually appealing? This one even looks directly at keyframes in pixel space.
3 critics. Interesting. Why separate them?
Because improving motion might sometimes conflict slightly with, say, pure aesthetic beauty in a still frame. Having separate critics lets them optimize for all these dimensions more effectively, balancing the trade-offs based on human preference data for each aspect.
And how do they use those scores?
This is the other novel part: base model feedback learning. Instead of just using the scores to train the reward models better, or using complex RL algorithms like PPO, they found a way to directly optimize the main video generation model to maximize the combined scores from all 3 reward models simultaneously. The sources claim this direct feedback loop into the generator itself is more efficient and effective for improving overall video quality across all these dimensions compared to other methods. They do it iteratively over multiple rounds.
Wow, directly tweaking the generator based on the critic scores, and they apply this to upscaling too.
Yes, super resolution RLHF. Many diffusion models have a base generator and then a refiner stage that upscales the output to high resolution. They applied this multi-critic RLHF process to the refiner itself. So the refiner learns not just to upscale, but to upscale in a way that specifically improves motion and visual fidelity according to human preferences, even when you're trying to generate quickly with fewer steps. That's pretty sophisticated feedback.
That is sophisticated. Layering human preference signals like that. Okay, all this training, architecture, data, it sounds complex. But the sources also talk up the speed and ultra-fast generation experience. How do they pull that off?
Yeah, speed is obviously key for making these tools practical. They attack this from several angles. On the DIT optimizations front, they use diffusion distillation. Basically, training a student version of the model that learns to reach a good result in far fewer computational steps than the original teacher model. They mention specific advanced distillation techniques like TSCD and score distillation, reportedly achieving significant speedups like 4x faster, allowing stable generation with very few steps, NFEs. They also adapt adversarial training techniques using human preference data to make sure the quality doesn't drop too much with the speedup.
Okay, so faster core generation, what else?
The VAE optimizations. Remember, the VAE decoder turns the latent code back into pixels. They designed a thin version of it, reducing the number of channels or internal pathways. This reportedly gave them a solid speedup, maybe 2x, just in that decoding step, supposedly without hurting the final visual quality.
And the hardware side?
Oh yeah, inference infrastructure. This is deep engineering stuff. Things like kernel fusion, combining multiple small computations into bigger, faster ones, using quantization, lower precision math, and sparse attention where possible. Developing smart strategies for splitting the work across many GPUs for long video sequences. Hybrid parallelism, context parallelism, using techniques like asynchronous offloading to handle memory limits, even optimizing the VAE distribution across hardware. It's a whole stack of optimizations working together.
Gotcha. It's not just the model, it's how you run it. So bringing it all together, data, architecture, training, speedups. How does Seedance 1.0 actually perform according to these evaluations? How does it stack up?
The sources paint a pretty strong picture. On public leaderboards like the Artificial Analysis Arena, as of the date in the sources, early June 2025, Seedance 1.0 was apparently ranked first for both text-to-video and image-to-video. They particularly noted a large lead in the I2V scores over competitors like VO3 and Qing 2.0 at that time. And they stress its performance as a unified model doing well in both tasks, which isn't always the case. Some models excel at one or the other.
Okay, leaderboards are one thing. What about their own tests?
They developed an internal benchmark, Seed Video Bench 1.0. What's interesting here is they say it was designed with input from film director experts. It uses a detailed evaluation taxonomy, subject accuracy, action realism, camera movement quality, aesthetics, and for I2V, how well it preserves the original image features, so quite granular.
And the human comparisons, head to head.
Right, they did human evaluations, both absolute scores and side-by-side comparisons, GSB. For text-to-video, Seedance 1.0 was up there with Qing 2.1 and VO3. The key finding highlighted was that Seedance 1.0 and VO3 showed superior prompt following capability compared to Qing 2.1 in these tests. And they argue that precise control is really critical for users.
Okay, neck and neck on quality, but better control for Seedance and VO. What about image to video?
For I2V, Seedance 1.0 and Qing 2.1 were the strong performers. The sources claim Seedance 1.0 matched Kling's motion quality, but again had better prompt following, especially for complex changes. They also noted that VO3 in their tests sometimes struggled to keep the characteristics of the starting image.
Interesting trade-offs there. Were there specific capabilities highlighted that maybe resulted from those architecture choices, like the multi-shot thing?
Definitely. Two things really stand out in the examples and discussion. First, multi-shot generation. That multi-shot MMDIT we talked about, it seems to pay off. They show examples where a single prompt generates a sequence with distinct shots, maybe a wide establishing shot, then a close-up, then a reaction maintaining coherence. This opens the door to more complex cinematic storytelling directly from text, things like cuts, match cuts, etc.
That's a big step beyond just animating a single scene.
It really is. The second capability is multi-style alignment. The model seems quite adept at generating video across a broad range of styles, photorealistic, black and white, anime, cyberpunk, you name it, without needing specific fine-tuning for every single style. That flexibility is obviously huge for creative work.
So practical applications, where might we actually see this technology deployed?
Well, the sources mentioned plans for integrations starting pretty much now, June 2025. Platforms like Dubao and Jiang are specifically named. The overall vision, they state, is for Seedance 1.0 to become an essential productivity tool, not just for high-end film production, but potentially for everyday creative tasks, too. The speed and control improvements are aimed at making it more accessible and useful.
Right, making it a practical tool, not just a research demo.
Exactly.
Okay, that really brings us full circle on this deep dive into Seedance 1.0. We've gone from the nitty-gritty of their data pipeline and that dense captioning idea through the architectural layers, decoupled attention, multi-shot ropey, into that really complex post-training with multiple AI critics and direct feedback, and finally the speed optimizations.
And I think the key point really emphasized in the material is that it's not one single magic bullet. It's the careful integration and optimization of all these different pieces, data, architecture, training, feedback, inference, that allows Seedance 1.0 to apparently achieve that strong balance between following instructions, believable motion, and high visual quality. That synergy seems to be the core of their approach.
So as we see models like Seedance 1.0 pushing these frontiers, faster generation, more precise control, better narrative coherence across shots, it makes you wonder, what kinds of totally new storytelling or creative avenues do you think this unlocks for people? Something to think about.